Reality doesn't exist until it is observed. The Infinite Observer asks us to imagine a universe that only becomes real when someone looks at it. In this video, we follow that audacious idea from quantum quirks to the vast architecture of space-time, revealing how observation might braid consciousness and existence itself. You'll see why this matters for time, causality, and what it means to know anything at all. If you're curious about how watching could influence reality, you're about to meet a perspective that makes the observer essential, not optional, the key to the whole cosmic story. The paradox of the infinite observer. The paradox of the infinite observer arises when we ask whether the universe requires an observer to instantiate its properties, and what that would mean if there were an unlimited number of observers across all regions of space-time. No outside witness exists. In quantum theory, measurement appears to select one outcome from many possibilities, and imagining an infinite set of observers amplifies the mystery by suggesting every potential observation might be realized somewhere. That spreads the question from a single measurement to a cosmology of experience. Different interpretive routes offer different answers, and the infinite observer forces us to compare how measurement, reality, and information are tied to conscious agents, instruments, and the broader environment. Decoherence helps explain why outcomes become practically definite. But decoherence trades a mysterious collapse for rampant entanglement with the environment, which means that the appearance of a single reality does not strictly require a conscious observer. The paradox remains when you push the scale to infinity. The infinite case pushes the dilemma into a realm where intuition about a single observer no longer suffices. Many Worlds treats every possible outcome as real in a branching multiverse, and the observer becomes a navigator of branches rather than a creator of a single fact. There is no outside vantage point in this view. Relational quantum mechanics reframes facts as relative to each observer, so what is observed by one observer need not be the same absolute fact for another, thereby dissolving the need for a universal observer. The infinite case tests whether such relativization can endure when the number of observers is unbounded. Cubism moves the emphasis toward subjective degrees of belief, treating the quantum state as a tool for an agent's expectations rather than a third-person property of reality. That makes the paradox about knowledge more than about the world. If there were an actual infinity of observers, the measure of observed outcomes becomes a technical issue, requiring careful definitions to avoid contradictions about probability and frequency. Ultimately, the paradox invites us to refine what we mean by existence, observation, and information. Historical conceptions of observation. Observation in ancient and medieval thought was primarily a process of gathering what the senses could report and interpreting it through established causes and purposes. Sensation and reason were bound together by teleological explanations. Aristotle framed what is observed as manifestations of form and purpose in nature. Scholastic commentators argued that reliable observation requires a framework of accepted authorities and demonstrative methods. In that world, observation wasn't just data. It carried explanations about why things happened, not merely how they looked. Thus, the observer was embedded in a network of traditions that defined what counted as evidence. The Renaissance and early modern period shifted confidence toward instruments, measurement, and experiment. Telescopes and microscopes expanded the senses, turning observation into an experimental practice. Measurements became central. Galileo's detailed celestial observations challenged received cosmologies by insisting that what we see depends on how we look. The instrument and the theory informed each other. Hypotheses guided what to observe, and observations reshaped hypotheses. This mutual dependence seeded a new ideal, observation as a disciplined engine for theory, not a passive mirror of nature. In philosophy and science, observation began to be analyzed as something more than raw data. Kant argued that the mind brings organizing concepts to sense experience, so what counts as an observation is shaped by the observer's framework. That claim reframed data as inseparable from interpretation. Instrumentalists and realists debated whether observations are unthematic signs of a real world or tools that merely predict outcomes. In physics, the rise of relativity and quantum ideas heightened the sense that measurement and observer context alter what is being described. Observers do not stand outside the phenomenon, they participate. The 20th century deepened the sense of theory-latedness and measurement-induced effects. Heisenberg's uncertainty principle formalized a limit to simultaneous knowledge of certain quantities, highlighting the observer's role in defining outcomes. Bohr's complementarity further argued that different experimental arrangements revealed different aspects of a system. Modern cosmology shows the same tension in practice. We infer the state of distant objects through models and data pipelines, not by direct touch. Decoherence, Bayesian inference, and the idea of the observer as an agent who updates beliefs connect historical debates with current methods. Together, these threads map a lineage where observation is never neutral, but a historical stance that has continually shaped what kind of universe we can claim exists. Defining the infinite observer. An infinite observer is a theoretical construct used to talk about how observation relates to the existence and properties of the universe. In practice, definitions split into several strands. In physics, observer often means the physical system that registers information, such as a detector or a measuring apparatus. In philosophy, the term can refer to a conscious subject or a collective of subjects. The infinite qualifier signals a limit case, an observer whose capacity, scope, and permanence exceed any finite or localized agent. This definition is not a single, settled position. It serves as a lens for discussing the connection between knowledge, measurement, and being. One practical way to frame it is as a boundary object that encompasses every potential viewpoint and every mode of detecting physical states. It treats observation not as a single act, but as an ongoing capacity to acquire and encode information. The infinite aspect is not about a person with limitless memory, but about an idealized limit where no finite observer can exhaust the universe's structural correlations. As a result, the infinite observer is often described as a conceptual horizon rather than a spatiotemporal agent. Different traditions tighten or loosen this boundary. Some identify the observer with the quantum measurement event. Others extend it to include apparatus, environment, and even observers across a cosmological scale. The key implication is that knowledge, measurement, and existence are entangled in a way that makes the very notion of a state meaningful only within an observational context. In Wheeler's participatory ideas, observation contributes to bringing aspects of the cosmos into being. In many worlds interpretations, the observer is part of a branching structure that coexists with alternative histories. Decoherence shows how interaction with the environment suppresses interference, yet it stops short of a universal, conscious act that collapses a state. The infinite observer could be imagined as an ultimate aggregator of all such interactions, a thought experiment device rather than a concrete agent. In information-theoretic terms, observation updates an observer's state of knowledge. The infinite version would update without bound as new correlations are found. Critics point out that treating observation as a metaphysical necessity reintroduces mystery about why matter seems structured in the first place. A practical critique notes that real observations can be modeled by physical processes without invoking a conscious mind. The infinite limit remains a helpful heuristic for questions about the role of information and structure, not a physically realizable agent. Using this concept can illuminate debates about realism, measurement, and the nature of explanation. If you're exploring it, keep in mind that it is an idealization designed to probe what observation might require, rather than a blueprint for building a detector. The discussion stays valuable as a way to map how different theories treat the link between being and knowing. The observer's role in shaping reality. In quantum theory, observation is defined as an interaction that extracts information from a system and, in many interpretations, selects a definite outcome from a range of possibilities. A detector, not a mind, can be the observer. The wave function encodes probabilities, and the act of measuring can influence which probability materializes. Reality appears through what is actually observed. In the classic double-slit experiment, particles create an interference pattern when no path information is available. Once a detector records which slit a particle passes, the interference vanishes. This shows that the mere possibility of knowing a system's history can determine whether a superposition behaves like a wave or a particle. Information governs behavior. Quantum eraser experiments demonstrate that interference can be recovered by erasing or altering which path information after the event. The outcome depends on how information is stored and retrieved. These results emphasize that the observer's role is about information pathways and interaction, not about conscious intention alone. A measuring device suffices. Decoherence describes how environmental interactions continually spread quantum coherence into many degrees of freedom, producing the illusion of a definite state without requiring a conscious observer. The world appears classical because interference terms fade. In this view, the observer is a junction of information flows rather than a single magical agent. The universe is a network of interactions. In some formulations, the infinite observer, Anabludathala, bis Katurva Nisisthe, is imagined as a participant grounding existence through information. These ideas are debated. In practical terms, science relies on well-defined measurement protocols, statistical inference, and repeatable experiments to distinguish actual effects from artifacts. Quantum technologies hinge on precise control of measurement and information. Implications for cosmology and ontology. The proposition places measurement and experience at the core of physical reality. In cosmology, this invites the question whether histories, constants, and even the fabric of space-time are fixed independently of observers or enacted through observation. John Archibald Wheeler framed a participatory universe where observers help bring the cosmos into being. While not universally accepted, this idea continues to shape discussions about boundary conditions, the nature of quantum states, and what it would mean for a universe with no external agent to observe it. Ontologically, it nudges philosophers toward a relational or information-centered picture rather than a simple collection of independent objects. Relational quantum mechanics argues that the properties of a system exist only in relation to an observer. The infinite observer intensifies that stance by conceiving a limitless network of interactions across the cosmos, where every measurement carving a fact into reality from a particular vantage. Different observers may report incompatible accounts of the same event. That situation reflects the core quantum principle that states are not absolute, but informationally grounded in the interactions that define them. Information is physical. Wheeler's maxim from bit crystallizes the position that information underwrites the existence of physical law, not merely describes it. Reality becomes a web of relational facts rather than a single, spectator-independent backdrop. In cosmology, an observer-centric view reshapes how we treat initial conditions and the calibration of constants, since properties may be understood as relational attributes tied to observation. Fine-tuning becomes a question of selection effects. The anthropic principle, in its weaker forms, is often invoked to explain why we find ourselves in a universe whose laws permit conscious experience. Multiverse explanations gain conceptual space here. If histories are actualized through observation within a broader informational field, then measure problems in cosmology reflect the challenge of assigning probabilities across observer-relative branches rather than a single global state. Empirical tests are difficult. Nevertheless, advances in quantum gravity and quantum cosmology seek to connect boundary conditions, horizon information, and observer-dependent narratives into a coherent framework. Practically, adopting this stance pushes cosmologists toward relational formalisms and information-theoretic constraints that tie what is observed to how it is observed. Laboratory analogs and simulations explore how observation may influence emergent properties. Thought experiments, such as nested observers and decoherence in closed systems, illuminate how an indefinite observer concept could influence expectations about cosmic history without asserting paranormal capabilities. The bottom line is a shift from objective absolutes to relative facts. In ontology, the infinite observer invites a stance where reality is not a fixed collection of entities, but a tapestry woven from interactions, information, and the conditions that enable observation itself. That view changes what we count as explanation and what we count as evidence. Open questions and debates. Observations in quantum theory occupy a tricky boundary between possibility and actuality. The central open question asks whether observation is a physical process or something tied to consciousness, and if the latter, how that maps onto equations. In practice, Physicists model observation as a physical interaction that transfers information and leaves a record, while the mathematics often treats the wave function as evolving unitarily until a measurement occurs. Decoherence shows how interactions with the environment can make superpositions appear to collapse into classical states, yet it does not by itself explain why a single outcome is experienced by an observer. Who counts as an observer? The boundary is hotly debated. A detector, a computer, or a brain? Where does the boundary lie between mere physical interaction and genuine observation? In decoherence-driven views, the environment itself acts as a pervasive observer by continually recording information and suppressing interference. Cubism treats the observer as an agent who assigns probabilities and updates personal knowledge after an action on a system. Relational quantum mechanics argues that properties emerge only in relation to a particular observer or system, so there is no absolute, observer-independent state to reference. Does observation instantiate reality or merely reflect it? The Copenhagen-like stance leans toward measurement, selecting a definite outcome from many possibilities, while many worlds posits that all outcomes occur in branching, equally real histories, and the observer becomes a node within that branching structure. Objective collapse theories modify dynamics to produce definite outcomes without appealing to a conscious observer, offering a middle path that avoids some philosophical pitfalls but introduces new physical assumptions. Thought experiments, such as the Wigner's friend scenario, underscore that different observers can disagree about what is real or certain, illustrating deep tensions in how facts are defined across reference frames and informational contexts. Cosmology and quantum gravity escalate these questions because there is often no external observer to anchor a theory. The problem of time in quantum cosmology and the idea of observables defined relative to internal clocks push researchers to seek observer-free or observer-relative formulations that still recover classical reality for anyone who looks. The relational or emergent spacetime viewpoints suggest that what counts as a universe's state may depend on the informational stance of the observer, not on an absolute backdrop. In parallel, holographic ideas and approaches to quantum gravity invite questions about where an observer sits in the fundamental description and how measurement is encoded in a theory where spacetime itself may be emergent. Experimentally, researchers push on nested and extended versions of Wigner's friend tests, delayed choice and quantum eraser experiments, and information-theoretic tasks that probe how agency, knowledge, and correlation propagate through a system. These investigations rarely settle a single interpretative answer, but they sharpen the boundary between what is considered an observer, what counts as measurement, and how reality might be constituted across scales. The debates continue to evolve as new architectures for quantum information and novel theoretical frameworks illuminate whether observation is indispensable to existence or simply a robust, contextual way of describing correlations within a larger, possibly observer-dependent, fabric of reality. We've traced the idea of the infinite observer from a spark of curiosity to a broader possibility, that the act of looking is not just a feature of science, but a thread weaving together measurement, meaning, and reality itself. We've seen how the observer isn't simply watching a fixed cosmos, but participating in its unfolding through interaction, correlation, and the stories we tell about what we see. We've weighed the quantum emphasis on measurement, the idea of decoherence that gives us a world that feels definite, and the philosophical whispers that suggest reality might be shaped in part by our attention. The through line is simple and staggering. Observation ties the fabric of existence to the act of perceiving it, and that link invites us to wonder what being present really means in a universe without obvious separations. If you felt that resonance, the sense that your gaze matters, that your questions are part of the physics you're trying to understand, you're not alone. Your attention, your curiosity, and your willingness to hold a question are part of the conversation that keeps this universe intelligible to us. And if a moment of stillness or a thought experiment during the video sparked a new angle or a stubborn doubt, that's exactly the outcome this exploration aims for. If this sparked a thought, consider leaving a comment with what you found most striking, or share a question you'd like us to chase in future videos. A like or subscribe helps this channel keep exploring with you. In the next installments, we'll test these ideas with approachable demonstrations, tease apart how time, information, and observation interact, and invite voices from physics, philosophy, and cognitive science to broaden the conversation. The journey continues, and your perspective is part of where it goes next.